Our next speaker is Joslyn. Cliff is the Chief Scientist for Knowledge Services in the Seattle office of PNNL. He's a mathematical systems theorist and computer scientist with research interests in discrete mathematics and applied order theory, cyber systems modeling, semantic technologies, and knowledge discovery and databases. He's currently PII for a really interesting project that I hope we'll hear some of.
Cliff Joslyn out of Pacific Northwest National Laboratory. There's a bunch of us here. I'm very pleased to say. I'm going to report to you today on some analytical research we've been doing. 25? That's not right. Give me the full 30, please. On a program in internal R&D, laboratory-directed research and development program called Asymmetric Resilient Cyber Security. Thank you. So I'm really going to talk to you today very quickly in my scant 30 minutes on 4 kinds of things. First, introducing the project and some of our test data environments that we're working with. Some looking at the basic graph statistics that we're doing inside NetFlow databases. And then 2 novel research directions we're taking. One looking at labeled degree distributions in NetFlow graphs, and the second looking at measures of time interval synchrony in NetFlow databases as well. So we begin a little discussion about our ARC project, Asymmetric Resilient Cybersecurity. As I mentioned, this is an IRAD, an internal effort, trying to look at the need for cyber systems modeling at a foundational level, looking at mathematical foundations and conceptual foundations for these digital systems where you can't bring your physics modeling to bear. There's no contiguity and continuity and conservation principles like mathematical modelers would in other domains. Instead, we represent cyber systems. Our goal overall is to represent cyber systems as multiple discrete mathematical objects that are interleaved with each other, combined in hierarchical coarse graining and fine graining, where you do validation across the levels. And to do so using discrete mathematical foundations, including, in this case, graph theory and labeled graph theory. So, in order to approach this very lofty goal, we make 2 initial assumptions, modeling assumptions. The first is to turn to this community in NetFlow as a first cut towards that. That is that the NetFlow databases and structures provide a terrific opportunity to aim at the middle layers where we can drill down to packet level if we wished, and we can also roll up to enterprise levels and other higher order levels as well. So there's the classic NetFlow graph that we're all familiar with at this point, which we represent. You're seeing a lot of these kinds of diagrams here that I'll represent conceptually. Notice I'm just showing a couple of octets and a conceptual port number, port 1, port 3, et cetera, and then the edges are adorned with, let's say, the number 3 there is just standing in for a total number of bytes or total number of packets, and then the interval indicating the time frame, the start and stop time for that particular flow. Our second modeling assumption is that we found a test data set, which I'll tell you about and which we're mining out for these particular efforts. The advantage of the test data set we're using, that's open, it's got ground truth, and it's a moderate size. These are the different data sets we looked at over time. There's more out there, and I think this community is familiar with most of these. The vast data set was actually reported out at last year's FloCon by Christy Whitley, and I'll show you some details on that in particular. A little bit more about our environment. We're currently scaling up to order 100 million edges in a Netezza twin-fin high-performance relational database environment, which is parallel using FPGAs. We're also using Tableau 8.1 for our exploratory data analysis. The graphs you'll be seeing are coming out of that environment. In the future, we're planning to scale up dramatically, moving into a high-performance graph database system that we're also building at PNNL as part of another project. So, the VAST data challenge. The VAST stands for the Visual Analytics Science and Technology community, which PNNL has been active in for a number of years. Working with our sponsors, they come to us and they say, hey, we really care about X or Y. Please develop some interesting test data so that the research community can pound against it and do something really cool. So from 2011 to 2013, that was in cyber. And so PNNL worked in a consortium that led the effort to build out a substantial NetFlow database simulating a particular sort of attack situation. Scenario is the company Big Marketing, and Big Marketing is a web server company that exists in a simulated internet environment, and then the challenge to the community was to do visualizations for situational awareness, and there were submissions from universities, commercial partners, et cetera. And they moved on to other things since then, but we've found this data set to still be quite useful. Basic structure is the company's internal servers are divided into 3 sites, which are conveniently denoted by IPs so we can see which ones they are. And then the external world sits across a firewall. There are detailed simulations inside each of the servers for performers of web servers, performance of workstations, et cetera. So a variety of IPs doing simulated behavior. And then a timeline over which those attacks would occur. So attacks occurred over a period of a week, DOS attacks, intrusions of other sorts, malware infections. Finally, the company wises up, they shut everything down for a weekend and come back with an intrusion detection system in place. And so you see different behaviors after that, but meanwhile there's all sorts of drama and excitement with things being infected and a lot of things happening. So it's a fairly rich environment, and we found enough good features and interesting things here to really occupy us for a while. We're now moving, of course, on to outside of test data and operational data, and it's going to get even more interesting, I know. So we look at NetFlow in the context of a discrete math fundamental kind of formulation of a collection of the standard features of the NetFlow. So if you simply look at the basics, flow count, what we call IPPs, which are the pairs of IPs and ports, as distinct from the IPs by themselves or the ports by themselves, the IPPs being sort of the cross product of those two. And then times, both the start time, the stop time, and the duration, payload number of packets, number of bytes, transport protocol, et cetera, then you're looking at a fair amount of computational complexity. Oh, by the way, all over input and output. So double all of these based on whether you're looking at ins or outs. You've got an awful lot of complexity there if you simply want to look at how features combine with each other to explain behaviors. Combinations are manifold. There's many combinatorially large number of things. Do I care about flow count together with start time? Do I care about IPs together with payload on either incoming or outgoing, et cetera? So there's so just doing basic statistics, graph statistics effectively over these structures, we think is providing a lot of value to people. And so I'll show here is just a couple of few cherry-picked examples that we've got from our Tableau interaction. And then we'll be concluding the talk with the discussions about the 2 new things we're doing, the degree distributions and the time intervals. So we begin by taking a perspective that comes out of a technical term called graph cubes, which is the desire to have sort of multidimensional projections, as you would in OLAP databases, to combine with graphs. So it's basically saying that if you've got, here I'm showing a NetFlow, a cartoon version of a NetFlow graph displayed with the IPPs, that is the IP port pairs as being the nodes. And you can do a roll-up operation, 2 different roll-up operations on them, one being the IP projection, where you combine together like these 2 edges, A.x1 and A.x3, with 1 byte here and 3 bytes there, means that I've got from A.x as a whole to B.x as a whole 2 links, which we show in red, and then you add together the 1 and the 3 to get 4 total bytes. So of course we're going to get a vast reduction in the size of the graph when you take the IP projection and correspondingly the port projection on the other side. These are both embedded subgraphs within this main graph. So we're looking at ways of moving around inside these projections of the graphs as a sort of fundamental operation. There's many other ways of doing it too, depending on how you built your graph in the first place and what kinds of features you have on the nodes and also on the edges potentially. So in that context, then, we can look at our test data set from VAST, 69 million total flows. And if you just look at the IPP graph, that is the IP port pairs in combination, 10 million of those IP pair ports. And that is beyond even what our high-performance systems can handle, not surprisingly. To get detailed statistics on each of those 10 million is going to be a computational challenge for anybody. So instead, we go and look at the IP projection, which goes down to 14, in this particular test data set, only 1,400 IPs, so that's a vast reduction. Also, the density increases from a tiny, tiny fraction, 0.00646%, up to a modest 1.57% density. You do the same thing over on the port side. We did do that over on the port side. I'm only showing 1 port graph here. We've got tons of other graphs that we could show if we wanted to engage with people, because there's 65, of course, 65,000 on the order here, and not as much density increase and not as much reduction in size. We did do some work over the port side, but we ended up working mostly on the IP side. So in that context then, looking again through our Tableau tool for EDA, you could do just some very, very basic things. And you can start look at flows, for example, against each other. On this graph, what we're showing, most everything will be log-log plots that you'll be seeing, so keep that in mind. So really vastly larger things out here in the upper right than in the lower left. What we're looking at here is flows in versus flows out, just the counts of the number of flows. Tableau has this beautiful ability to show multidimensional data using color, using texture, using size, as well as the two axes. And here what we're doing is we're breaking out the color coding that the blues are the externals. Remember, these are the guys that the big marketing is communicating with. And then the orange, green, and red are the three internal servers that we show, those three big blocks. So you can see here that these, in fact, these IPs, 172.30.04, 20.04, 10.04, these are, in fact, the big servers themselves. And they show very high number of flows in, also very large number of flows out, more flows in than out, which I came to learn, not being a cyber guy proper until somewhat recently, that's, of course, because web traffic is initiated from an outside client, and then that becomes an incoming flow, even though the massive data is, of course, going out because of the way that the data is, the way that request is initiated. As distinguished from all of our external guys up here, which is the reverse, and in fact what we found, and you'll be seeing in other plots, is that the bulk of these guys, in fact, are our attackers. These are the ones that are doing the DOS attacks and the other attacks coming in. So right away, you're able to just get a sense of how things break out. You've got groups of workstations down here and other sorts of things going on. This is a tool, in other words, an exploratory tool for analysts to be able to interrogate their data. This is the same plot, but now for ports. So obviously port 80, our big friend up here, 123.25, pretty much what you'd expect. This is broken out by ephemeral versus non-ephemeral. So the oranges here are ephemeral, this little group of non-ephemerals at the top there. We didn't drill in too much into this. In fact, there's so much complexity in this data that a lot of times we're simply doing literally exploratory data analysis, meaning let's look at it and see what we see. And sometimes things leap out and sometimes don't. It also depends on how much time we spend with the experts, with the analysts who own this data and work with it. Okay. So, oh yes, let's see if we got the movie. Yes, we get the movie. Bryan made this wonderful movie for us. So this is another example of what we can do at the basic level with Tableau. So it's a somewhat complicated plot. The movie will loop here so you can get a, uh-oh. Don't know what happened there. Let's see. Try that again. Hopefully this will, I got a single screenshot after this in case we have to resort to it. Look quick before it blacks out again. How's that? Okay, on the, okay. We'll just look at this one. Fortunately, I had one in the oven already. And so what we're looking at here is on the x-axis, the total well, first of all, excuse me, each point is an IP, right? So for each IP, what we're showing is the total outgoing payload on the x-axis, and on the on the y-axis is, I always forget, yes, the total number of outgoing flows. It's not shown on the axis, I'm afraid, but it's total number of outgoing flows here, and then outgoing payload there. So these are my big outgoing guys. In this case now, I'm sizing by, what I'm doing is I'm sizing, rather, by incoming payload. So what you saw, on the brief moment you saw the movie there, you saw this is marching through day by day, and you're seeing this distribution of normal activity, and then you see that one point blooming up to very high level of incoming payload. You'll also notice that it's a circle, which means it's an external. So this is some site outside of us that's taking a large amount of internal incoming payload. That's an exfiltration event. And we're able to see the exfiltration event occurring over the course of just looking at the movie. And then we go back and say, oh, we have access to the ground truth, and we can see that, in fact, there was an exfiltration event there. So that's really good for us to see. And again, we haven't done anything fancy at all, just taking the basic graph information and running it into our, through our Netezza into our Tableau. And then we did a bunch of other things. But these are some of the most exciting things that we were able to see. So I'm going to move on now and talk about the two new ideas that we've been pursuing. First is motivated by the idea that simply looking at, if you're looking for anomalies, you're looking for features, you're looking for patterns of behavior, that we have access to a lot more information, of course, than just volume. A lot of tools and metrics out there. I mean, flow volumes are important, of course. We wouldn't say otherwise. Number of flows and total payloads. But we think we can do better than that. This is, we're very pleased to find this work from few years back by Lakina and Kravala et al. and where they were making, years before we were starting, they were working into the space as well, making some good observations. So for example, of the different kinds of anomalies, flash crowds, port scans, network scans, et cetera, that they were finding there's lots of different features that can distinctively identify different kinds of attacks. Now, identifying attacks and patterns of attack isn't the only thing we care to do. Certainly for our program, it's not the only thing that we're focused on, but it's certainly a good way to start in terms of being able to bring diagnostic features for behavior detection and event detection of different sorts, state detection, if you will, of different sorts. So here is some example data that they were using where you're looking at flow data here, number of bytes, number of packets, and you're not seeing the actual behavior. What we're seeing here is the entropy of the destination IP and the entropy of the destination port, where you're seeing a very low destination IP entropy and a very high destination port entropy, really marking where the attack actually occurred, distinctly from the numbers of flows. And I'll unpack that for you in a minute to tell you what that actually means. So packets and bytes aren't always sufficient. IP and port behavior can tell the difference. This is a port scan that's going on here. So in order to attempt to move into this, we want to start to look down inside the graph and ask questions about the distributions of, in our case now, the IPs. This also works for ports. We've done it for ports. So again, back to our basic formulation. How can we characterize the relationships between IPs, ports, et cetera? How many of them are talking to each other, and in what combinations and in what ways? How is that discussion distributed? So if you fancy yourself as a node in your graph, and let's say that I've got a bunch of incoming flows and a bunch of outgoing flows. I'm an IP. I talk to all these IPs. I've got 4 flows coming into me that are distributed over 3 IPs. So you basically construct a basic count distribution. 2 are coming from C, and 1 each is coming from A and D. On the outgoing, similarly, 2 are going to B, and then 1 each from A, C, and E. If you forget about directionality for a moment and simply look at any edges that are touching this, then I can say that I got 3 touching me from C, 2 from A, 2 from B, and then 1 each from D and E. That is the distribution, count distribution of the IPs on incoming, outgoing, and undirected. And we can analyze those in terms of label degree distributions of the corresponding graph, get a sense for the count of who is talking to whom and in what ways. We have 2 distinct measures that we bring to bear. First, we call it dispersion. And dispersion is basically a log ratio of the number of IPs on either incoming or outgoing that another IP is talking to relative to the number of flows. I'll show the math in a minute, and I'll show you some examples as well. So the first one's called dispersion. The second one is called smoothness. Dispersion is just about the number of IPs you speak to. Smoothness is about their distribution, whether it's even or lumpy, and that's measured as a normalized entropy. So some examples. So here's a little distribution. This is 10 different flows that are distributed into 2 buckets. They talk to 2 different IPs. In this case, 6 in one and 4 in the other. Sorry, the numbers are small, but that's up to 10 here at the top. So 6 to one and 4 to the other. So that's got a small dispersion of 30, because you're going from 6 flows down to 2 IPs, and a very high smoothness, almost 100% smoothness, because they're very evenly distributed. If you increase the dispersion, you might go to a distribution like this. It's now distributed over 5 IPs, not over 2. So the dispersion increases up to 0.7. The smoothness is now completely at 100% because you've got exactly 2 in each one. Or you might have it coming from the other direction. This distribution up here has the same dispersion, note, 0.7 as this one, because it's also distributed over 5 IPs, but the distribution is very lumpy. So it's got a lower smoothness than the completely smooth one. So this picture hopefully illustrates the 2 concepts. We verified mathematically that these are somewhat independent of each other, as you can see just from this example. So you need both coordinates, basically, to measure the shape of your distribution. This is the math. A log ratio for what we call kappa, which is the dispersion, and G is our relative entropy, which is a smoothness. We also, for the mathematically inclined, come talk to me later, and we can talk about integer partitions and measures in integer partitions, because that's a lot of fun too. So we think that smoothness and dispersion really need to interact together in these kinds of measures. We know that smoothness is definitely significant because Lakina et al. have demonstrated that. Their measures of the entropy of source IP and destination IP is exactly that, and they're able to show sufficiently statistically significant differences from looking at source and destination IP across different kinds of attack patterns. The single bullet indicates 1 degree, and the stars represent 2 degrees. distinctions. And they were demonstrating that before. It's effectively the same kind of measure we're using, not exactly the same. For our purposes, it's close enough. So we know that we want to work with smoothness, but we want to go further because we think our dispersion, which we know is independent of the smoothness, also adds great value. It's simpler computationally, first of all. All you got to do is count numbers of buckets. You don't have to worry about the actual distribution itself. We know mathematically that it's necessary together with the smoothness, and we've early reason to believe that it's actually potentially more significant than smoothness on an operational basis. And we'll show you a couple of examples. Here's one right now. So what we've got here is we're showing for the output only, we could do it for the input too, but for the output only, we're showing the dispersion along the x-axis and the smoothness on the y-axis. Again, each point is an IP. They're color-coded the same way that the blues are the externals and the other colors are the internals of different sorts. And now they're also sized by the number of flows going out. So a couple of things we're able to see right off the bat is that we've called out here, actually, some of the significant attackers. These aren't all the attackers, but there's some of them. They're in the external sites and they're outside, and they're marked all by having a very small outbound dispersion. And what that means is they got a massive number of flows that's going to a very small number of IPs, because they're doing focused attacks on just a few servers inside the enterprise. But notice that, so they're all on the left, basically, because they all have a small dispersion, but they're distributed along the axis because they have different smoothnesses with respect to that dispersion. So entropy alone isn't going to get you that. You need this other measure that we're using, counting the number of buckets, basically. And we'll give you a couple of examples of that. So here's, for that particular point up there, 10,222, we've got 1.7 million flows that are distributed over only two IPs, and they thus get a 97%, a tiny fractional dispersion. Kappa is our measure for dispersion. So a microscopic dispersion, but a very high G because they're distributed quite evenly with 1,700,000 across those two IPs. The next one down, on the other hand, 10 million flows now. Notice that the size of the dot is much larger. 10 million flows, also distributed over two IPs. Again, a microscopic kappa, but now the G is substantially higher because while it's only over two, they're distributed in a 9-to-1 ratio. So again, it's a more uneven distribution. And the two statistics together can start to tell you that story of both how many and what's the shape of the distribution they're talking to. And then finally, 1.7 million flows here, distributed over 6 IPs. Again, a very small kappa, not quite as small as these others, because we do have this now long tail of, small tail actually. It's not a very long tail, but a bit of a tail, let's say, of other IPs that are also being engaged with, 70, 71, et cetera. So you have to ask, if that's really that kind of an attack, what else is going on? You could divide that by time scale, or there's other ways of looking at that. So we're seeing that that dispersion by itself, first of all, adds to what the entropy dispersion smoothness can give you, and that they also work together. Here's another example. Here we've got the inbound dispersion against the inbound number of flows. This is for a denial of service attack. And we're able to see that our victims are all up here, again, with very small inbound dispersions, very large number of inbound flows. The two in orange are the ones we knew about, and the one in gray is the one we didn't know about. And it popped out to us when we actually looked at it in this plot. Of course, number of flows is still significant, don't get me wrong. Obviously, you can just look at that, you don't even need our stuff. Its number of flows may or may not get you to that realization just by itself. Okay, last on this topic then, we also have, we could look at it in a timeline. This is Tableau. It's really able to do this stuff quite nicely. So this is the entire exercise. This is the 2-week simulated time frame. And each of these lines corresponds to a particular IP. And what you're seeing here is color coding. In this case, we're color coding by dispersion. So blue is low. And we're also showing volume on the x-axis, or on the y-axis, excuse me, is volume for inbound on top and outbound on the bottom. So you're seeing that we're seeing very low dispersions for all of these attacks which have these very high flows. Labeled out here, we're calling out the port scans, the denial of service attacks, and the rest of that. But correspondingly, for the smoothness, the port scans have a high outgoing dispersion, or excuse me, high outgoing smoothness and a corresponding low incoming smoothness as opposed to the denial of service attacks. So that speaks to the different structure of the behavior of those two kinds of attack plans. So I'll close out the talk now with some discussion of the second new analytical thing that we're doing, which is regarding measures of time interval synchrony. We spent more time doing some of the fundamental mathematics here, and Unfortunately, our vast data set wasn't quite as illustrative of some of these creatures as we would like. We're able to work out some things going on in VAST, but there are artifacts and other reasons why it's not quite what we would like. So we're trying to move on to look at some other data sets as well. We've got some interesting things to show here, but honestly, we're looking forward to working with new data that either has a finer resolution on timescale. We really need to go down to 100 millisecond times, or more coherent behavior. Be that as it may, it's still pretty interesting to look at. So first of all, we go back to our basic NetFlow graph, and so far we've been looking at things like payload sizes and the ports and IP connections. We can also look at the time intervals that are associated amongst the edges. So here's a particular IPP, which is connected to other IPPs, and you can take the intervals that represent their times, and you can show, display them graphically here. And you can see there's some complicated structural relationships, and you can also see that there's both series and parallel connections. Both series and parallel connections. So for example, I can look at AZ3 and AZ2. These two flows are in a parallel connection with respect to CX2 versus a serial flow that's going through from AZ2 to CX2 up to BX1. So all of those are present here. There's different ways of breaking these apart and looking at graph motifs and looking at the way that the intervals interact with each other. Here's a ton of math about how we do some of that stuff. For our purposes, it's sufficient to recognize that, looking at the picture, it's sufficient to just recognize that we've got generally three qualitative kinds of behaviors for the way that two intervals can interact with each other. It might be that they're a disjoint, so that there's an actual gap between them. This one completes before that one begins. It might be that they properly overlap, so that this one starts, then the next one starts, then the first one ends, and then the second one ends. And it might be that one's nested inside the other. There are some edge cases dealing with when you've got equal endpoints and stuff like that, but for our purposes, this is close enough to being the three things that you can do with two different intervals. Beyond that, we can also do things like you can union over them, you can take the average of them, there's lots of operations you can do, and you can also do this thing we call separation. And what separation does is it returns an interval quantity, which is the minimum distance versus the maximum distance. So how close do they ever get versus how far apart do they ever get? How close do they ever get depends if they overlap. If they overlap, then of course they get zero apart. There's some points that are the same. And then, so the minimum separation here is 0. The maximum separation is just, how far apart the outer side is. And that's an interval value between the biggest and the smallest. We can look generally at the distribution of durations, and what we're actually seeing here, this is what I mentioned before, the inadequacy of this particular data set. We got a ton, that's a log plot, of very small durations. That's because we weren't able to go down to millisecond durations, which we really need to do. So that's the problem with VAST. There are too many short flows. I also wanted to mention Lee is in the audience somewhere. Lee's going to be talking tomorrow about her encounter complexes, which is a way of, for the ones that are disjoint from each other, you have a tolerance parameter, which allows you to identify certain edges as being actually next to each other if they're separated by a simple minimal amount. I've illustrated that here, but she'll tell you all about that tomorrow. But we like that, and we're going to try to use that for ways of simplifying some of these graph structures so we can do this better. All right, I'm running out of time here, so we'll look at the distribution of the, in fact, I've got so little time that I'm going to skip, I think, a couple of things. This is the distributions of the three different qualities. It's kind of hard to explain and not all that interesting, so on that basis, we'll skip right to the end. And this is a particularly difficult computational exercise because it's quadratic. You have to compare all these edges against each other, right? So you got to do full quadratic of all the flows against each other. So instead we tried that a bunch and tried a bunch of ways to reduce the size and focus and lots of different things. But in the end, we decided we needed to go bottom up, focus on particular known attacks, and then look at the behaviors within those contexts. So what we've got here is a particular DOS attack. This is a botnet DOS attack, meaning an internally infected site is doing a DOS attack to the outside. So what we've got here now is the blue is my externals that are the victims now of the attack. And they've therefore got a ton of incoming flows on the externals, a ton of outgoing flows on the internals. You'll actually notice that there are a collection of lines here overwriting each other because they're working in synchrony, because it's multiple machines that are infected and doing the attacks. And so this is just incoming flows and outgoing flows. Down here, we're starting to look at this time interval stuff. This is the average outbound duration of the attackers versus the attacked. And this is the outbound maximum separation. So what we're able to see there is that during the course of the attack, which occurs over about 3 hours, this is our time scale, that the two things happen. First of all, of the attackers, the duration is shrinking, but then it's not just that the duration is shrinking. Additionally, the separation between them, this maximum separation between them, is also decreasing in a synchronized manner. So that's because these infected machines were all turning together and focusing on their target in a way that their processes were synchronized. So this is just one example, and there's not a ton more to be said about it, but it's indicative of the kind of structures that we're looking at, the kinds of measures that we think might be available, especially if we can increase the computational productivity of these kinds of measures. So that's great. I just hit a minute. And so thank you. As I mentioned, this is an initial research effort with test data. We are, in fact, transitioning some of this to operational status, engaging. We're also, recall that I mentioned we were interested in multi-scalar, that is hierarchically structured graphs. We're doing the same analysis now, starting to look at login graphs. We're also porting to our high performance capability, and we're eager to collaborate with whoever is interested. So thank you.
All right, I'll take a shot. So you had two metrics that you spoke quite a bit about. One was dispersion and one was smoothness.
Yep.
Do those apply to a general probability distribution, or do they depend on discreteness?
They actually, the subtlety here is that they apply not necessarily to probability distributions, but to frequency. That is not relative frequency, but absolute frequency, that is count distributions. The normalization you need to go to turn a count distribution into a probability distribution is why people have not done this before, because everybody begins with a probability distribution. Mm-hmm. So you need to start with those raw counts. That's the way that you normalize. Means it's, well, this is maybe not a good idea.
Okay.
Well, I think I can do this very fast.
Do you have a slide with the actual definition?
Yeah, so this is the math slide.
Okay.
And what you can see here is that this lattice that I'm showing here is the lattice of all of this is the integer partition for the number 6. This is all the ways you can take six things and divide them up. And there's a bunch of different probability distributions that are in there normally the way you work at probability distributions is you don't assume a fixed count. Mm-hmm. Right? In other words, 0.5 is a probability distribution. It could be 100 or 1,000.
Sure.
And so you can't distinguish those. So this method will allow you to distinguish those.
Okay. Thanks.
Very good. Thank you.